In this mini tutorial, we're going to think about the principle of moments and how this applies to the function of joints. So let's start off by drawing a very simple seesaw. So this triangle here represents the fulcrum of the seesaw, that being the place where the hinges where the seesaw revolves around. And here is the seesaw itself. Now, we can imagine that at the two ends of the seesaw there are two people sitting. The force generated by the person sitting on the left hand side can be represented as going in a downward direction, and we can call that F1. So that's the force of person number one. On the right hand side we could have another person sat, and we can call that F2. So this is the force exerted by the second person at the end of the seesaw. Furthermore, we can consider the distance that each person sits from the fulcrum. So on the left hand side here we have this distance, and we can call this D1, and on the right hand side we have this distance, and we can call that D2. Now, it can be shown that if we multiply the force by the distance from the fulcrum on each side in a balanced system, that is in a seesaw which is not rotating, which is in balance, the product should be equal. So we can say that F1 times D1 equals F2 times D2. And this is only the case when the seesaw is balanced. So what we're going to do now is to extrapolate this idea of a seesaw to an actual joint. And the example I'm going to use is the elbow joint. So here I'm drawing the humerus, here I'm drawing the ulna, and this is the olecranon of the ulna going out and ultimately articulating with the wrist and the hand. Like that. Okay, so here we've shown a very crude diagram of the elbow joint, and let's try to fill it in like we did for the seesaw. So the fulcrum is at this point here. This is where the fulcrum is, where the joint hinges. F1, the force F1, we can think of as the force with which the triceps muscles pull on the olecranon. So this is force F1. Force F2 we can think of as basically a load which you're having to carry in your hand. So that's going to be generated through the hand itself. So this is force F2. In terms of distances, distance D1 is from the centre of the joint to the tip of the olecranon, and distance D2 is from the centre of the joint to the tips of the fingers. As we showed earlier by the principle of moments, in the case of a system in equilibrium, i.e. where there's no rotation occurring at the joint, F1 times D1 should equal F2 times D2. Now let's try to consider a situation where we wish to maximize the load which can be lifted during elbow flexion. That is, we wish to maximize the value of F2. So if we rearrange this equation, we get that F2 is equal to F1 times D1 all over D2. And if we stop to think, if we wish to maximize F2, that is, if we wish to maximize the force with which we are able to extend the elbow, we can do a number of different things. We can maximize F1. That is, we can make the triceps muscles much more powerful. Alternatively, we can maximize D1. So therefore we can make the olecranon longer. Finally, if we wish to maximise F2, we could alternatively minimise D2. That is, make the length of the forearm much shorter. And this is actually what we see in joints where we wish to develop very high forces. And it's seen in the most extreme examples in animals which dig, so animals like aardvarks and moles. In the case of aardvarks, moles, armadillos and the like, what you notice about those animals is that they have incredibly long olecranon processes. They have very, very powerful muscles and are very muscular animals in general. And in general, their limbs are very, very short, thus enabling them to maximise the amount of power that they can use to dig through soil. And you can also use these insights from comparative anatomy when considering the human body. So to give another example, think about the calcaneum in the foot. This is quite a long bone projecting posteriorly. And this tells us that the movement of plantar flexion is very, very powerful. And you know that that's a powerful movement because it's so easy for you to stand on your tiptoes. If your calcaneum was shorter, you'd need much more powerful calf muscles to stand on tiptoes. So I hope this short mini tutorial has been useful, and as always, it would be much appreciated if you could leave some feedback. Okay, thank you.